Welcome to episode 460 of AI Brief. I'm your host, Amin.
And I am your expert guide, Leah.
Today we are handing you the ultimate shortcut to being completely well-informed. If you want to understand the forces actively reshaping our reality today, you are in the exact right place for this deep dive.
We have a very dense, fascinating roadmap for you today, covering both the macro and the micro levels of where technology is heading.
First, we will unpack a massive tectonic shift in the global AI chip market led by Huawei. Then, we explore some mind-bending breakthroughs in the physical sciences. This includes the successful transport of antimatter, the potential discovery of an exploding black hole, a completely new solar energy barrier being shattered, and finally, a beer made from thin air.
We will then close out with a rapid-fire breakdown of today's top trending AI tools that focus heavily on true digital autonomy.
We are tracking a fundamental evolution. We are moving from observing our technology to letting it take the wheel. And the physical infrastructure supporting that technology is transforming at the exact same time. Let us start with that foundational hardware.
The physical brain of artificial intelligence is it's undergoing a monumental shift right now.
Huawei has reached a major milestone with its new Ascend 950PR AI chip. And we are seeing Chinese tech giants, specifically ByteDance and Alibaba, preparing to place massive orders for this hardware.
They've concluded their testing phases, which is a big deal. They are now explicitly shifting toward this domestic hardware to, bypass the tightening U.S. export restrictions on NVIDIA processors.
And the timeline is incredibly aggressive. They are moving into mass production next month in April 2026, with full-scale shipments expected in the second half of the year.
The target is an astonishing 750,000 units this year alone.
Which is huge.
Yeah.
But the specifications of the Ascend 950PR are what make those numbers so impactful, right?
Yeah.
It's not just a general chip.
No, not at all. It's a specialized processor optimized specifically for AI inference and model execution. And that distinction is absolutely crucial for understanding the market.
Break that down for us. What is the difference between training and inference?
So training an AI model requires this raw, brute force computational power. You're processing trillions of data points over months. You can think of training as the AI getting its university degree.
Oh, I like that. So it's the learning phase.
Exactly. Inference, on the other hand, is what happens after the model is trained. It's the execution phase. It's the day job.
The day job. So it's the AI actually answering your prompt or generating an image or making a calculation in real time.
We got it. So optimizing for inference means Huawei is explicitly targeting the everyday, extensive deployment of AI applications across millions of consumer devices.
To help visualize this massive shift, imagine the global tech ecosystem as a transcontinental railroad. For years, companies worldwide have been buying their locomotives from one primary supplier.
The tracks, the signaling systems, the maintenance tools, the training manuals, all of it was built around those specific trains.
Right. And what Huawei is doing here isn't just offering a different brand of train. They are building an entirely separate, parallel railroad system from the ground up.
And that is incredibly difficult to do because of the software layer. But reports indicate the Ascend 950PR offers improved compatibility with existing software ecosystems.
Which makes it much easier for developers to migrate away from NVIDIA hardware. So I have a pointed question about this. Does this improved compatibility mean the software moat previously held by U.S. firms is effectively evaporating?
The short answer is that the moat is certainly shrinking at a highly accelerated pace.
Wow.
The longer, more complex answer is that we are witnessing the fracturing of the global AI supply chain in real time. For years, the dominance of Western hardware was cemented by the software layer built on top of it.
Because developers learned those specific proprietary tools and migrating away was just prohibitively expensive, right?
Right, and incredibly time-consuming in terms of rewriting code. By prioritizing software compatibility, Huawei is essentially lowering the drawbridge.
So moving from just testing these chips to extensive deployment across companies the size of ByteDance and Alibaba, that means this market is no longer hypothetical.
Not at all. We are accelerating rapidly toward two independent, competing global AI ecosystems. The hardware, the software, and the end-user applications will run on entirely separate, parallel tracks, completely walled off from one another.
This massive pivot to parallel AI infrastructure brings up a glaring issue for the future, which is power. Training and running these dual ecosystems is going to require an exorbitant amount of energy and a really deep mastery of physical sciences.
It absolutely will.
So let's slow our pace down for a second here. We are transitioning now from the macro engineering of the global AI supply chain down to the microengineering of fundamental reality.
The implications of these next few breakthroughs require a much more deliberate, measured look.
At CERN, scientists have achieved something that took more than a decade of preparation. They loaded 92 antiprotons into a cryogenic trap, secured that trap to a truck, and drove it 6.2 miles across their campus in Geneva.
Which is astounding because antimatter is arguably the most fragile substance in the known universe.
It annihilates the moment it comes into contact with regular matter, right?
Yeah. Instantly. If a single antiproton touches a single molecule of air, it vanishes in a burst of energy. For decades, this extreme fragility meant antimatter was entirely landlocked.
It was permanently trapped inside the highly controlled, massive laboratory environments where it was originally created.
Yes, freeing it from that fixed home is profound logistical and scientific achievement.
Transporting it feels analogous to trying to carry a delicate soap bubble through a hurricane in the back of a pickup truck. You are moving a substance that desperately wants to annihilate itself, using a vehicle that vibrates over roads that bump through an atmosphere made entirely of the exact material that will instantly destroy it.
That is actually the perfect way to visualize it. To protect that soap bubble, they built a cryogenic trap that acts as a flawless magnetic and thermal isolation chamber.
So it suspends the antiprotons in a vacuum using electromagnetic fields.
Yes, so they never touch the walls of the container. Successfully moving those 92 antiprotons 6.2 miles proves the isolation technology actually works in transit.
And the immediate goal is to eventually move this antimatter to specialized facilities in Germany.
Because those facilities offer much quieter testing conditions. They are completely free from the intense magnetic and physical noise generated by the massive CERN accelerators.
And in that profound quiet, scientists hope to finally measure the fundamental properties of antimatter.
To answer one of the biggest outstanding questions in physics, why matter survived the Big Bang at all, rather than being completely canceled out by antimatter in the first milliseconds of the universe.
It is incredible, and from the absolute smallest particles trapped here on Earth, we look out to the most massive, destructive forces in the cosmos.
This is a wild story.
In 2023, an underwater telescope located off the coast of Sicily detected a neutrino. But this wasn't a standard particle. It was orders of magnitude more energetic than anything human beings have ever produced in a particle collider.
And now, scientists at MIT believe this highly energetic neutrino may be the first real proof of an exploding black hole.
Wait, back up. I have to admit some confusion here on behalf of the listener. How does a telescope sitting at the bottom of the ocean in Sicily see a black hole exploding in deep space?
It sounds impossible, but it is a brilliant piece of engineering. Neutrinos are often called ghost particles because they pass straight through almost all matter. Trillions of them are passing through your body right now.
Trillions.
Literally trillions. Because they rarely interact with anything, they travel in perfectly straight lines across the universe. But when a highly energetic neutrino occasionally crashes into a water molecule in the deep, dark ocean, it creates a tiny flash of blue light.
Oh, I see. So the underwater telescope is essentially a massive grid of light sensors waiting for those specific flashes in the pitch black.
Exactly. And tracing the trajectory of that flash points us directly back to the source. This connects directly to a theory proposed by Stephen Hawking in 1974.
The classical understanding of black holes is that they only consume, right? Their gravity is so intense that nothing escapes.
Right. But Hawking theorized that due to quantum effects near the event horizon, black holes should actually emit a tiny amount of radiation.
Over vast cosmic timescales.
Yes, and this emission causes the black hole to lose mass, shrink, and eventually explode violently.
An exploding black hole has never actually been observed. So if this underwater neutrino detection is confirmed to be the result of that process, the implications for physics are staggering.
It would definitively validate Hawking's 5-decade-old theory. Furthermore, analyzing the particles released in that final, catastrophic explosion could crack open the mystery of dark matter and reveal entirely new, previously unknown particles to science.
We bring that cosmic energy back down to our terrestrial grid. A team of scientists at Kyushu University has broken a fundamental barrier in solar energy capture.
They have achieved a solar energy conversion yield exceeding 100%, officially hitting 130% quantum yield.
Stop right there. I have to push back on that. 130% yield sounds fundamentally incorrect. It sounds like it violates the basic laws of thermodynamics. How does a solar panel output more than 100% of the energy it takes in without crossing into impossible perpetual motion territory?
It is a critical distinction to make, and your skepticism is exactly where most physicists start. The system is not creating energy out of nothing, which would absolutely violate physical laws.
Okay, so what is it doing?
Instead, it is maximizing the extraction of the energy that is already present. Traditional silicon solar panels suffer from a major inefficiency. When a high-energy photon from the sun hits the panel, it typically only dislodges one electron to create a usable charge.
And any excess energy carried by that high-energy photon is entirely wasted as heat.
Exactly. The Kyushu University team utilized a process called singlet fission. Think of a standard photon like a bowling ball hitting exactly one pin, representing our electron.
So all the extra momentum of that heavy ball is wasted as it rolls into the pit.
Yes. Singlet fission essentially turns that bowling ball into a cluster bomb halfway down the lane, splitting its energy to knock down two pins instead of one.
I see. So the 130% figure refers specifically to the quantum yield, the ratio of charge carriers produced to the number of photons absorbed. You're getting more energy carriers out of the system than the discrete number of light particles that went into it.
Precisely. You are extracting the wasted heat energy and converting it into a second usable charge.
The research is currently in the proof of concept phase, though.
It is. However, if this singlet fission process can be scaled for mass manufacturing, it represents a pathway to push real-world solar grid efficiency far past the hard physical limits of current silicon panels. We could generate significantly more electricity using the exact same surface area of sunlight.
Fixing the power grid also means fixing our carbon footprint, which brings us to applying this extreme terrestrial science directly to everyday human enjoyment.
This is perhaps my favorite update today.
Almanac Beer Company, located in California, has debuted the world's first beer carbonated with carbon dioxide pulled directly from the atmosphere. They've installed a capture system right inside their Alameda brewery.
The system actively pulls in ambient air, isolates the CO2, and refines it to an incredible purity level of 99.9999%.
This is a highly practical solution to a very real supply chain vulnerability. Brewers acutely remember the national CO2 shortage of 2022.
Absolutely. Commercial CO2 is heavily tied to the fossil fuel supply chain. It is overwhelmingly captured as a byproduct of industrial ammonia production.
By capturing CO2 from the ambient atmosphere, they completely bypass that fossil fuel dependency.
And if this microcapture technology proves economically viable for a local brewery, the blueprint exists to scale it for broader applications.
It paves the way for fossil fuel-free operations across agriculture, commercial food refrigeration, and even the curing processes used in concrete manufacturing.
Managing these new complex carbon and energy systems alongside entirely new parallel hardware ecosystems is going to require tools that operate much faster than human hands.
Which means the landscape of artificial intelligence tools is evolving rapidly to meet this exact need. The overarching theme across all of today's trending applications is the transition from AI as a passive chatbot to AI as an active, autonomous agent.
We are upgrading the technology from an advisor who simply gives you written instructions to a digital intern who actually takes control of the mouse and clicks the buttons for you.
We will break down today's 8 top trending tools that illustrate this shift. Let's unpack Claude computer use first. Giving an AI control of my actual mouse cursor feels wild. How is it fundamentally doing that?
It uses advanced vision language models to essentially watch your screen. It takes rapid screenshots, maps the exact coordinates of your user interface, and executes click and keyboard commands exactly as a human operator would.
That is incredible. So you can instruct it to complete complex, multi-step tasks across entirely different, unconnected desktop applications, and it navigates the workflow seamlessly.
Yes, it bridges the gaps between your apps.
Then we have Littlebird. This is an AI assistant designed to already possess the deep context of your work.
Right. Instead of requiring you to upload files and explain your current project parameters every single session, Littlebird maintains continuous context vectors.
It has an ongoing, active awareness of your workflows and documents, so it never starts from zero.
For building custom, autonomous solutions, we are seeing the rise of highly specialized agents. Tabira.ai is a fascinating example.
This is a network entirely populated by AI agents actively hunting down deals and negotiating purchases on behalf of their human users.
It executes the logic of a procurement officer. It is doing the actual negotiating.
Agent-Place AI agents is another one. It allows users to construct bespoke agents tailored for very specific real-world workflows.
You are building discrete digital workers for discrete operational tasks, defining exactly what triggers their actions and what their outputs should be.
As these agents take on more work, We need tools that allow continuous operations without constant human bottlenecks. Auto Mode by Claude Code focuses precisely on delegating permission decisions.
Instead of an AI halting its workflow every 5 seconds to ask you for authorization to modify a file or execute a script, Auto Mode allows you to delegate those minor permission gates. It enables the AI to work continuously in the background.
Venn.ai operates on a similar principle of delegation, but focuses on strict functional boundaries. It allows you to hand over real complex work to AI agents while setting absolute technical parameters.
You define the exact access control list and system boundaries of what the agent can and cannot modify within your network architecture.
With autonomous agents taking action across these systems, oversight becomes the final critical piece of the puzzle. Secker is an observation and analysis tool built specifically for this new paradigm.
It monitors the API calls and execution paths of your deployed voice and chat agents, providing deep analytics on how they're actually performing in the wild.
Finally, we have agentation. As agents execute tasks invisibly in the background, users need to understand what is happening without reading endless lines of code.
Agentation provides graphical visual feedback mechanisms, allowing you to see a clear dashboard representation of exactly what your AI agents are doing at any given moment.
The architectures behind these 8 tools prove that we are no longer just talking to our computers.
We are deploying digital workforces that can see, reason, negotiate, and execute complex workflows across entirely independent applications.
This brings us to a critical synthesis of everything we have unpacked today. Consider the trajectory you are on. We now possess the technology to pull carbon dioxide directly out of thin air to carbonate our beverages.
Simultaneously, we're willingly handing over direct, functional control of our computer systems to highly autonomous AI agents that can navigate our desktops and negotiate on our behalf.
The capabilities of the physical world and the digital world are compounding at an extraordinary rate.
We are rapidly moving toward a future where our physical climate infrastructure, our advanced solar grids, and our atmospheric resource management systems will require the kind of rapid, complex oversight that only autonomous AI can provide.
Because human operators simply won't be able to process the variables fast enough.
Exactly.
Which leaves you with this provocative thought to consider. If the software mode is evaporating, and massive tech companies are migrating their foundational hardware away from Western supply chains, how long is it until we hand over the autonomous, active management of our entire physical climate infrastructure to these new, highly capable AI models running entirely on non-Western hardware?
The shift from observation to autonomous action is happening in every sector simultaneously, from silicon manufacturing to deep space astrophysics. Understanding the underlying mechanisms behind these currents is exactly how you navigate what comes next.
Thank you for joining us for this deep dive. If you value staying ahead of the curve and unpacking the actual mechanisms behind the headlines, follow the show and share it with someone who shares your curiosity for the future.
See you in the next episode.